All right, welcome. We see fire, we use it, we definitely fear it. But have you ever really stopped to think about what fire is? I mean, really, it's not just some magical, destructive force. It turns out it's a fascinating and, believe it or not, predictable scientific process. So let's dive in and really unpack the chemistry of fire.
Okay, so let's get right down to it with that big question. Is fire a solid, a liquid, a gas? Is it even a thing at all? The answer might actually surprise you. It's one of the most common things on our planet, but it's also, for sure, one of the most misunderstood.
So what is it? Well, if you look at official definitions, like from fire safety codes, they give us a huge clue. They call it the active principle of burning. Now, the key words there are active principle. This isn't defining an object, you see. It's defining an event, a process that's happening.
And that's really the key takeaway here. Fire isn't a substance you can bottle up or hold. It's a rapid, self-sustaining chemical reaction. It's something that happens to stuff, not a type of stuff itself. And once you shift your thinking to that, everything else starts to make a lot more sense.
A really cool way to think about this process, combustion or burning, is that it's the exact opposite of photosynthesis. Think about it. Plants spend years slowly, patiently taking in the sun's energy, building themselves up, and storing all that energy in their wood. Fire does the complete reverse. In just minutes, it rapidly breaks all of that down and releases all that stored up energy as the heat and light we see.
Okay, so if fire is a process, what does it take to get it started? For a long, long time, the go-to explanation has been what we call the fire triangle. Just think of it like a super simple 3-ingredient recipe. So your recipe needs 3 things, all at the same time. You need some fuel, anything that can burn. You need heat, that's the spark, the energy to get things going. And you need oxygen, which is just all around us in the air. It's kind of like a 3-legged stool. If you take away any one of those legs, the fuel, the heat, or the oxygen, the whole thing just falls over. The fire goes out. And what's kind of wild is you don't even need that much oxygen. I mean, the air we're breathing right now is about 21% oxygen, but most fires, they can keep on burning with a concentration as low as 16%. That's exactly why smothering a small fire with a blanket or a lid works. You're just cutting off its access to the oxygen it desperately needs. Now, the type of fuel makes a huge difference, too. You've probably noticed this yourself, right? Trying to light a big, solid log with a match is almost impossible. But a small pile of wood shavings or paper? Poof, it goes up in an instant. It all comes down to surface area. The shavings have tons of surface area exposed to all that heat and oxygen, so they ignite really fast. The log, on the other hand, is so dense it needs way more sustained heat to get that process started. Okay, wait a second. This brings up a really big question. Just look around you right now. You're surrounded by fuel, your desk, your chair, the clothes you're wearing, and there's heat all around you. And obviously, there's oxygen. So, if the fire triangle is all it takes, why isn't everything just bursting into flames all the time?
And that's where the simple triangle model starts to fall apart. It's because it's missing something, a crucial piece of the puzzle. We need to talk about the hidden 4th element, the real secret ingredient that keeps a fire going.
That missing piece? It's something called the chemical chain reaction. This isn't just another ingredient. It's the engine of the fire. See, as the fuel burns, it releases heat, which then ignites more fuel, which in turn releases more heat. It creates this self-sustaining loop. Without that chain reaction, you might just get a quick flash of heat, but you won't get a lasting fire.
So, to get a better picture, scientists and firefighters don't really use the triangle anymore. They use a more complete model, the fire tetrahedron. A tetrahedron is basically a pyramid with 4 faces, and each face, fuel, heat, oxygen, and that chemical chain reaction, is touching all the others. It's the perfect way to show that all 4 are totally dependent on each other. If you remove any one side, the whole structure collapses.
All right, so now we know what fire is, but how does it move? How does it travel from one spot to another? Well, the key to that is understanding how heat, one of the sides of our tetrahedron, gets around.
Basically, heat gets around in 3 main ways. First, you've got conduction. That's heat transfer through direct touch. Think of a metal fireplace poker. The handle gets hot, even though it's not in the flame. Then there's convection, which is heat moving through gases or liquids, like all that hot air rising from a candle flame. And finally, radiation, which is heat traveling through space in invisible waves. That's how you can feel the warmth of a bonfire, even when you're standing several feet away. Now, of those three, you really have to watch out for convection, especially inside a building. As all that hot air and smoke rise from a fire, they hit the ceiling and start to spread out, filling the room from the top down. This creates a superheated layer that can ignite everything in a room almost instantly. It's an invisible superhighway of heat, and it's exactly why firefighters are always taught to stay low to the ground. Okay, so why are we digging into all this chemistry? What's the point? Well, it's because when you understand the science, fire stops being this mysterious, chaotic force. It becomes something predictable, and most importantly, it becomes something controllable. So let's just nail down the big takeaways. 1, fire is a process, a chemical reaction, not a thing. 2, that process absolutely needs all 4 sides of the fire tetrahedron to work, which leads to the most important point. To stop a fire, you don't have to fight the whole thing. You just have to be smart and break the tetrahedron. Take away the fuel, cool down the heat, cut off the oxygen, or interrupt that chain reaction. That's it. And knowing how heat moves helps you predict where the fire's going next.
So in the end, fire isn't chaos. It's a process that follows a predictable set of rules. It has a recipe. And understanding that recipe doesn't just make it less scary, it empowers you. So, I'll leave you with this. The next time you see a campfire or even just a candle flame, look a little closer. You're not just looking at fire. You're watching chemistry in action. Now that you know its recipe, how does that change the way you see it?